Well, let's walk through why this happens with both of these chemicals. So what we saw with the calcium chloride here on the left is as we added it to the water got a lot warmer, it got a lot hotter, which means that the water was absorbing energy. That's why it was getting hotter. Over here, the water's getting colder, which means the water must have been releasing energy. Next slide. So the water was getting hotter, and over here, the water was getting colder. And it's important that we remember that's the water, that's not the chemical, because we wanted to know whether the chemical was absorbing or releasing heat. Well, so imagine over here, if the water's getting hotter, that means that the water must be absorbing energy. You could imagine if I pick on this little chemical piece right here, this little bit of calcium chloride, it seems like the energy is going from the calcium chloride, into the water. The water has a Q that's positive, right? It's absorbing that heat. That's why we're seeing this temperature go up. That must mean that energy is coming out of this chemical as it does this reaction. So that means if energy is coming out of this reaction, then Q for the chemical is negative. The white particles are losing heat. They're exothermic. So this chemical reaction is exothermic. Just like over here, when we dumped in the powder and we stirred it, the temperature went down and down and down. That means that the water was losing energy. Energy was going from the water into the chemicals. From the water's perspective, Q was negative. It was losing that energy. That's why it was getting colder. And from the chemicals' perspective, it was absorbing that energy, and Q was positive. It was absorbing energy, so we know from the chemicals' perspective, this was endothermic. It was an endothermic reaction. Now that's a pretty darn cool thing that we took two powders, and I hope you caught this really kind of interesting bit, which is the water was about at room temperature, the chemicals were at room temperature. How the heck did the chemical warm up the water? Or over here, how did the chemical cool down the water if it wasn't cold? I mean, I know if I throw an ice cube in there, that water is going to get cold. But the chemical was not cold. How did it do that? And that's the question we have for this lesson. But let's summarize this before we get to the why part. Reactions that release energy are exothermic reactions. Makes sense, right? Anytime energy is going out, it's exothermic. And reactions that absorb energy are endothermic reactions. And we had two examples of chemicals that did reactions, one of each one. Now we do have some new ideas in this unit. You saw me just a moment ago say that Q from the calcium chloride's perspective was exothermic, so energy was leaving it. That was a negative sign. And that Q for over here, since it was endothermic, was positive. Well, in reactions, we don't typically use Q like we do with just hot objects like those metals. We tend to use the symbol delta H. And you already know that this means change. But we would just say delta H is negative. Over here, the delta H is positive for an endothermic reaction. And you really can say delta H. But delta H is said other ways. Delta H is the symbol for enthalpy. And all enthalpy is heat. Except for it's heat as it's applied to reactions. So if you're not just talking about a hot object, if you're actually talking about a reaction, we say enthalpy. This is the enthalpy or delta H of the reaction. So sometimes you'll hear people say it's the enthalpy of reaction. They're just talking about delta H, but using words. Or they'll say it's the heat of reaction, and they're just talking about delta H. Same thing, different ways to say it. And delta H really, really is the same as Q. The signs will be the same. If the heat is exiting, it'll be negative. If the heat is entering, it'll be positive. It really is the same as Q, but for reactions we use enthalpy, delta H.